So a small internal architecture we can see over here. It's a 64 cross 1 ROM with two-dimensional decoding. So we're going to have 3:8 decoder, 3 inputs and 8 output lines are going to be present over there, and we're going to have a 8:1 demux to select the outcome over there, which is going to be constructing a 8 cross 8 diode array. So the presence of diode makes logic 1, then the absence of diode makes logic 0. Such a way we are going to have this internal architecture of a 64 cross 1 ROM with a two-dimensional decode. So almost looks like an square chip. Coming to the next one, the internal architecture, how it's going to be present. So we are going to discuss about 2 to the power of n cross b ROM structure. So 2 to the power of n decides the number of input address lines. So if you're going to say that A0, A1 to n minus 1 lines will be present, which is going to be connected to a ROM decoder. Through that, it's going to be storing to the storage array. And chip select and enable pins are going to be present over there with a column multiplexer. With a column multiplexer, we are going to take the output from D0 to D of b minus 1. So if you're going to see about a summary of this ROM type, so it consisting of different types we have come across over the mask ROM, PROM, EPROM, EEPROM and flash. The technology which is going to be used in the mask ROM, or maybe a CMOS technology or NMOS technology, which is going to be in metal oxide semiconductor structure, and it may be available in the bipolar also. So the read cycle of this particular FET architecture, metal oxide semiconductor, it's going to be 22 to 200 nanoseconds, and in the case of a bipolar, it's going to be lesser than that of the 100 nanosecond. So write cycle time, it can takes 4 weeks, and obviously if you're going to see about that, the CMOS technologies are going to be a lower power, as well as a bipolar is going to be in high power and low density. Coming to the PROM, which is available in the bipolar technology, which is having an read cycle of 100 nanoseconds and 5 minutes for the write cycle, and the write once only. It's going to be only once we can write with a high power, and no mass charges are going to be needed over here. And the erasable programmable read only memory available in the MOS technology, NMOS and CMOS technology. The read cycle is going to be 25 to 200 nanoseconds and write cycle 5 minutes time. It's a reusable one which consumes low power and no mass charge is going to be needed for this. The fourth one, electrically erasable programmable read-only memory, which is going to be available in NMOS technology, which has 50 to 200 nanoseconds of read cycles and needs 10 milliseconds per byte, and it can be reused 10,000 write locations per limit is going to be present over there. Coming to the flash cards, which are available in the CMOS technology, which needs 25 to 200 nanoseconds of read cycle and 10 milliseconds per block, and it may be erasable cycles may be 100,000 times we can erase and we can reuse it such a way which is going to get available over here. So in general, if you're going to compare the memory in terms of 3 parameters, characteristics called as speed, size and cost. So a big challenge in this design of a computer system is to provide a sufficient large memory with reasonable speed at affordable cost. So if you can see about that, the SRAMs are going to be very fast, and the size is going to be a larger one, and it's going to be an expansive. And DRAMs are slower, and it's going to be a small in size and less expansive. Comparing to the magnetic disk, much slower than the DRAM. Actually, the speed is going to be much lower than the DRAM, whereas available in a small size as well as the low cost. So a small tabular column which is going to be explained about the characteristics of this particular speed, size and the cost for the SRAM, DRAM and the magnetic disk. Moving on to the memory hierarchy. The memory hierarchy here, which consisting of always it's going to be having a highest priority for the registers. The main memory can be built with the DRAM. Thus, SRAM is used in smaller units where the speed is going to be an essence. So what happened here, the cache memories are going to be two types. One is going to be a primary cache and one more is going to be a secondary cache. So usually if you're going to see that one, the memory is implemented using the dynamic components SIMM, RIMM or DIMM. The access time for a main memory is about 10 times longer than that of the access time of the L1 cache. So this diagram which is going to be explained about the particular thing. A fastest access is to be data held in the processor, always in the processor register. So what happened, always registers are going to be at the top of the memory hierarchy, and along with that a small amount of cache is going to be implemented on the processor chip. This is going to be called as cache. This is going to be called as a cache level 1. So level 1 cache is on the processor always, and the level 2 cache is going to be present in between the main memory and the processor. So in between this main memory and the processor, the secondary cache is going to be present over there always. The next level is going to be the main memory, which have been implemented as SIMMs, such larger but slower than that of the cache memory. Then the next is going to be an magnetic disk secondary memory, which is an huge amount of inexpensive storage. So usually speed of memory access is going to be critical. So the idea is to bring the instructions and data that will be used in the near future as close to the processor or as possible, so that what happened, the speed may be increased, the cost per bit is going to be get increased, and size may be get reduced. So let me compare the speed, size and memory, the characteristics with this particular memories over here, memory hierarchy. So if you're going to see about this memory hierarchy, the registers, primary cache, secondary cache, main memory and secondary memories are going to be present over here. So when compare this particular characteristics of speed, size and cost for this particular memory, registers are always very high, lower size and very lower in cost, whereas the cache memory, primary cache is going to be in highest speed and lower size as well as very low in the cost also. The secondary cache is going to be a bit lesser speed when compared with the primary cache, and it's going to be low in size as well as cost also going to be low. The main memory, usually we can say that the main memories are going to be always slower than that of the secondary cache as well as the primary cache, and the size is going to be somewhat a bigger one as well. Because of the size bigger and the area is going to be bigger, the cost is going to be high. The secondary memories are going to be very low in speed and it may be very high because of the size is going to be very high. Huge memory data can be stored over there, hence very high in size, as well as the cost is going to be very high when compared with the other memories. So these are the characteristics comparison of size, speed and cost for this all memories: register, primary cache, secondary cache, main memory and secondary memory.